This is Design Safe Radio, where natural hazards researchers strive to make our society more resilient to everything nature throws at us.
And so, and your part in this to transition to where you fit in is the non-structural component. So we talked a bit about the structure,
Correct.
How the floors and the walls and the diaphragms and the energy dissipation elements, but then you get to things like stairs, like, and the things that make a building livable in that are not part of the structure but still extremely important. So what are some of those components of the building and the questions that you're hoping to answer about those?
Non-structural components is a blanket term, basically represents all parts of the building that are important for its function, but not part of the load resisting systems, not part of carrying the gravity loads or the earthquake loads. So examples of non-structural components include non-structural walls, stairs, elevators, ceiling system, piping, equipment, any mounted equipment, etc. There's quite a number of different types of non-structural components. The earthquake engineering community historically has focused mainly on structural design, and we have a pretty good handle on that and what we can do to minimize damage in the structure and prevent collapse or even get better performance. But in past earthquakes, a lot of the damage is focused on non-structural systems. And I think the last major earthquake we had in the US, the Northridge earthquake in 1994, majority of the damage was non-structural. And that really got everyone's attention. And so we have started to focus a little bit more on non-structural components. So for this project, the team knew they wanted to have an emphasis on non-structural components as well. And it's a great opportunity. So I was recruited for that role, and I kind of had an open book. What do you want to do here? And we decided, since it's a flexible building, Tallwood, we wanted to focus on drift sensitive components, those that are basically connected floor to floor and therefore get subjected to the lateral movement of the building. So we focused on non-structural walls and stairs. I do want to acknowledge my students from UNR, my 3 PhD students. They're all on site here today as well. William Roser, ENG, and Sir Lathan Wynn. They're wonderful. We couldn't do this work without them.
Glad you mentioned that, because a lot of the kind of grunt, tedious work of these big projects is done by the graduate students.
Absolutely.
And, we couldn't do any of this without them. So you've got stairs, you've got cold form steel, non-structural walls. Do you have elevators in this building as well, or just the stairs? Okay.
Just the stairs.
I mean, just the stairs. But
just the stairs. The stairs are essential, of course, so why not make them part of the research?
Yeah, exactly. So what are some of those big questions you're hoping to learn about those pieces in this shake?
Right. You mind? I'd like to describe our exterior wall subassemblies. So go ahead and share again. This is a Revit model of the bottom stories of the building. The Revit model was done by another student from Colorado School of Mines, Alicia Bush, who works for Shiling Pei, who's the PI of the project. So we decided to do, we didn't have the resources to clad the whole building. We decided to focus on sub-assemblies, we call sub-assemblies, each one detailed a little bit differently so that we can compare how they perform. And each one of them is designed with some thought to how we can accommodate the movement in the building. One on each corner, basically. In the next visual, you see kind of a snapshot of a single story. So 3 of the sub-assemblies are cold form steel framed. They could also be wood framed, but the cold form steel industry was interested in participating in this test. So that was
go with where the resources are sometimes.
Exactly. So we labeled those cold form steel sub-assemblies. We labeled them CFS1, CFS2, CFS3. The first one is platform framed. The second one is bypass framed. The third one is spandrel framed. I'll explain a little bit more about each of those.
Mm-hmm.
And lastly, we have a stick-built glass curtain wall. So this is how these work. CFS1, the first one, is an L-shaped subassembly on one corner of the building. It is platform framed, which means that it bears down on the floor below. So it's connected, singly connected, separate units floor to floor. And the way we allow it to move is by having a slip joint at the top of the wall.
Oh.
And there's two different, basic CFS framing. You got a track on the bottom, a track on the top, and then studs connected in between. You can kind of see the outline.
Kind of like
here.
a big French door.
Yeah. So if you connect everything rigidly, it's not going to move. It's going to get damaged in the movement.
Right.
So a slip track, call it a slip track connection at the top, allows the relative movement. Basically, it's a form of seismic isolation. Back to my roots.
Yeah.
We're isolating the wall, the non-structural wall, from the movement of the building. Okay, so the one way that we're exploring is, we call it a double track. So you have two tracks at the top, they're nested, and the slip occurs between the two tracks. They're not connected together.
So just like a sliding door.
Yeah, that's one detail. And then the other detail, this is a product of CEMCO's. It's a slotted slip track. So there's slots in the track in the top. So, and it's going to be connected through screws into the slab, but not, tightly connected. And
so those screws will ride in those slots.
Exactly. The slip is designed to occur between the floor slab itself and the slots. Now, what happens at the corner? Because this visual down here gets a nice visual of the problem. When you accommodate the slip in plane, there is an incompatibility with what happens out of plane.
Right, you got a big space in the corner there.
The corner wants to open or close. So that's where CS Groups comes in. They make a series of, they have a wide variety of different expansion joints, and we are using one of their expansion joints at the corner to accommodate that movement. Okay, the second one is a bypass frame system with drift clips. Bypass frames means that instead of bearing on the floor below, the whole system is like hung on the outside of the building. So,
oh, wow.
Yeah, it's hung from those floor panels. And
whoa.
If it's rigidly connected, it's not going to move in an earthquake. And here's an image. We're going to use Simpson StrongTie's, one of Simpson StrongTie's products here, this DSS CB clip. It fits into, apologize, this is not a wood slab, it's visual, but it's utilized in wood. And they did a test for us to kind of understand the capacity. It's a unistrut attached to the floor slab, and then the clip sits in the unistrut and is attached to the stud, and the clip can slide in that unistrut.
Oh, wow. Okay. So that whole big panel can move and slide around in that strut system.
Correct. So on this one, we designed 3 stories bypass framed. Which is a lot, because the expected movement over 3 stories is about 10 inches.
Wow.
And we went for the gold here. Like how tall of a bypass unit could you get to be successful here? This sketch by my student William Roser illustrates what happens when at the corner over this 3-story unit, right? The drift gets, or the displacement incompatibility gets larger on each story. So for this one, we're using another expansion joint from CS Group, XLP2G1400, and it accommodates, it's like a door system almost. They have some illustrations on their website of how this one works. It's like it can pull apart, or if the joint pushes together, like the door flaps out, like shown in this
Oh, yeah.
image
That's
on the
really
left.
cool. Thanks for listening to today's episode of Design Safe Radio. This show is sponsored by the National Science Foundation, grant number 2129782. You can subscribe to Design Safe Radio on iTunes, Stitcher, or wherever you find your podcasts. Please leave us a review so that we can improve the show and also help others find our episodes in iTunes. Thanks for your feedback and support. We really appreciate it. You can find out more about NHERI at designsafe-ci.org, on Facebook at Design Safe Radio, or on Twitter at NHERI Design Safe.